at MIT, and she seemed interested in helping, and she wanted to put it. Extraordinaire at Harvard, and his students, David and Zillow, and then the seven of us spent about a year working on a project that would culminate in this paper. I think in the introduction there was mention of a lot of papers, and I have a lot of papers, and none of them I were proud of this paper. So this was a lot of work. I think we did a really good job, and it wasn't easy, but it was certainly interesting. We found something like that in the Atlantic Center that all three of these papers had found, but we were able to say a lot more about the details of the signal than we could before. An app like this is the raw app, and we managed to separate the signal from micro in a way that we were just something like this. A couple of things that are really interesting about this one, this is just how circular here this stuff. It doesn't elongate along the electric plane. You don't see much of their point sources or other confusion. It's very, very low speed signal. I think we managed to pull it apart pretty well. And if you just take this part of the signal and look at the shape of the spectrum, so this is the energy of what's going on, and this is how bright they are, and it looks just like it there. That's why it's so you're seeing something that in terms of the distribution of the sky and in terms of the energy distribution, one of the center theory that we're looking at. supersymmetric model, or is it part of a model of extra dimensions? Is it a consequence of a sort of grand unified theory that explains all the matter and force, what varieties of matter and force that we detect in the universe? Maybe that's something to do with quantum gravity in some way I can't currently understand, or any number of other things. The point is that every time you discover a new type of matter or energy, it gives you a better idea of how they all fit together. Just like any time you take one new puzzle piece, the more you see damage that might have been elusive otherwise. So I see us right now at an important turning point. It may be that a few years from now, we'll all be convinced that this was really just some sort of mundane astrophysics. Maybe there are 10,000 pulsars that were behaving differently than we expected, and that provides a good explanation for the data. But if I were a betting man, I think that's probably unlikely. I think it's pretty likely, not a guarantee, but pretty likely, that we're really discovering a new fundamental type of subatomic particle in the galactic center, and that this probably takes us a lot of dark matter in our universe. And that's the most exciting thing that's ever happened in my career, and I hope you find it exciting too. We may be finally sticking our head through the filament and seeing the universe a little bit closer to how it really is. Thanks for your attention. I'd love to take some questions. it will help guide us towards some sort of bigger theory. So maybe it's a particle that fits cleanly in a theory that we call supersymmetry, and then maybe that would help us understand how granular diffusion might work, and how quantum gravity might work, where the dark matter is a particle traveling through extra dimensions of space. That might have something to do with string theory, for example, etc. I'm only speculating, but the hope is that the more we discover about the kinds of matter and energy that can take shape in our universe, the closer we are, the closer we have to figuring out the underlying theory, the grand unified theory, or the theory of everything that underpins it all.
I was wondering, when you're thinking about these kinds of radiation signals coming from near the galactic center, are you presupposing that there's some kind of clear production of particle and antiparticle and dark matter? And if so, why are you confident that the same kinds of fundamental conservation laws that give rise to
analogies, but I don't think I'm going to give you a very good answer. I mean, if you're trying to put together a puzzle, the more pieces you have, the more you can get the underlying picture. One more piece might be what kind of particle makes up dark matter. I could give you a different kind of example, and this was supposed to be an illustration. So in theories we call supersymmetry, there are many, many other kinds of particles that exist. And if you were to start to discover some of those, and maybe dark matter might be one of those, you might figure out that there's this new pattern in nature we call supersymmetry, and the space-time behaves in this particular way. And then maybe you'll discover some more aspects of that, and you'll see that it fits nicely into something we call grand unified theory, and that will get us a lot closer to understanding some of the reasons for why things behave the way they do. And then maybe someday with that information you can build upon it and look for some sort of theory that ties that in with gravity, something we call a theory of everything. But who knows? Going back to the history of science, when any number of phenomena were observed for the first time, when the electron was discovered, did anyone know that it would lead to quantum field theory? Or when people were doing experiments on the speed of light, did they know that this would lead to relativity? Or when to begin to contemplate gravity, did anyone realize that it would somehow allow for the unification of the thing that pulls stuff towards the Earth and the thing that holds stars and planets in orbits? So I'm not going to presuppose that I can tell you how this is going to play out, only that that's the way science works. And the more you know, the more likely you are to be able to build a bigger theory that explains more.
This is like really simple compared to all the other questions, but I'm not quite sure why. I understood like why the star spins when they're faster when it's like more condensed, because like, I know like it has to have like some force acting when it's like spins. Like in a motor, electromagnetism causes the axle to spin. So yeah.
Great. So it's the idea is this quantity called angular momentum. Okay, and this is something that's conserved. So unless you touch something, you can't give it more or less angular momentum. And if you're big, if you're wide and spinning slowly, you have the same amount of angular momentum as if you're small and spinning quickly. Okay. So you've seen the figure skater, right? So they pull in their arms to spin up, to speed up. So by pulling their arms in, or the star collapsing, in order to keep the same amount of momentum, they have to spin and start going faster. Trying to think of other examples. Go to a merry-go-round. Take all of your friends, put them on the edge of the merry-go-round, and then get it spinning, okay? And then all at the same time, pull yourself to the middle of the merry-go-round. You'll suddenly start to go faster. Do that experiment, and then you'll understand.
Dr. Hooper will be up in the atrium to answer any more informal questions. There's a reception, lunch and cookies up there. And thank you once again for coming to Fermilab. experiments, plans for future experiments, and plans for future particle accelerator projects both at Fermilab and around the world. Hence, it's appropriate to have a forward-looking talk this evening. Our speaker is Dr. Sean Carroll, who is a theoretical physicist at the California Institute of Technology in Pasadena. Sean specializes in cosmology, gravitation, dark matter, dark energy, and many other areas of cutting-edge physics research. Sean is the author of 2 popular books that you might want to check out. In fact, I saw a few people in the audience getting autographs from Sean. They have great titles, these books. The first is From Eternity to Here, The Quest for the Ultimate Theory of Time. And the second, more recent book is The Particle at the End of the Universe, How the Higgs Boson Leads Us to the Edge of a New World. Sean's title tonight has a similar nice ring to it. It's forward-looking, and the title is Particles, Fields, and the Future of Physics. So please join me in welcoming Dr. Sean Carroll for this evening's talk.
Thanks. It's very, very good to be back here at Fermilab, where I spent many, many hours of my life in one of the best places to do physics and think about physics in the world. And as I was just talking earlier to some of the Fermilab folks, they said that many of their public talks are not about particle physics. They just use them as an excuse to talk about all sorts of fun things in science. And I know that nevertheless half of the audience is particle physicists because of the big meeting here, so this might be the most demanding public talk audience I've ever actually had the pleasure to speak in front of. But I have the benefit of having good stuff to talk about. Particles, fields, and the future of physics. Particles, you know what that is, you know what the future of physics is. Secretly, my hidden agenda that you can't get away from because you're here now is to do quantum field theory. That's what I really want to teach you tonight. So I'm very glad that Fermilab is giving me these 6 hours to really give you enough of a taste of what quantum field theory is really all about. So I was lucky enough last July 2012 to be spending my Independence Day in Geneva, Switzerland, at CERN, where it was a rock concert-like atmosphere. There was this event, it was planned, the announcement went out, people lined up, people camped out overnight, literally. It looks like people camping out before a rock concert, except there are a lot more Macintosh laptops in the audience than otherwise. And there was no rock concert the next day. There were